Good morning, and it's the mic work? Yeah. Mic doesn't work. So it's a very nice meeting, and I hope it will continue for many years, and we will have some 100th meeting someday. I'm going to talk about a system which is called Ehrenfest gas. This work is done in collaboration with two students, Sanjay Maudgal and Sarthak Chandra. These are undergraduate students who are now in Princeton and Maryland, respectively. So what we have, so Ehrenfest gas is a collection of particles moving freely in a plane and colliding with polygon-shaped scatterers, which are randomly placed. So this is a random Ehrenfest gas. If these scatterers become circularly shaped, that is called a Lorentz gas. So that's a very well-known system. And for Lorentz gas, we know that the dynamics is completely chaotic. That is, the single particle dynamics is completely chaotic. This is Ehrenfest gas. So, and here the dynamics is not chaotic. Each time there is only collision with a straight edge. And so there is at best an algebraic decorrelation in time. And so the Lyapunov exponent is exactly 0 in this system. And in around 96, 97, there were experiments carried out at Snowbird in Utah by Pierre Gaspard and collaborators, some colloidal systems. And they found that there is a connection between diffusion observed there and the classical single particle motion, which is chaotic. And they were trying to check, verify a formula which is called escape rate formula. And so they observed diffusion and tried to claim that that diffusive behavior is due to the presence of single particle motion, which is chaotic. No. These are randomly placed and randomly oriented. Polygons are completely fixed. These are, yeah, fixed scatterers. Yeah. So there is a large collection of particles which are streaming across this whole system. So they are all colliding, and one is trying to see how is the transport occurring as time passes by. So, so these papers on the experiment were published in Nature in 1998, and in 99 there were a series of comments again in Nature with simulations which said that if we replace the circular scatterers, which are Lorentz gas, by polygonal scatterers, we still get diffusion, although the Lyapunov exponent is exactly 0. And so there has been an important question around how is it, what exactly is the way to quantify the kind of non-integrability or an exponent for systems that are polygonal scatterers. And so in this few minutes, I'm going to show you that there is a way to define an exponent which is correct, most probably, and which goes to the Lyapunov exponent for the case of Lorentz gas in the limit of the number of sides of this polygon going to infinity. And for this, so we have to modify the collision rule. So the collision rule for a circular scatterer is well known. This was given by Gauss in 1841. So there is this incoming beam. This incoming beam has a radius of curvature which is given by rho minus is before the collision. Rho plus is the radius of curvature after the collision. After collision, there is this defocusing beam going out. We can extend this and define a radius of curvature. This rho plus and rho minus are connected by this formula, which is very well known, and the phi and a are specified. Sorry? Straight lines, I mean the beam has, this is like a wave front. So if we can draw a circle. So we are looking at the same time, how are these points situated here and here at a fixed time. So we have a radius of curvature. So the collision law is written in terms of radius of curvature. Okay, beams are incoming and outgoing. And similarly, one can do some geometry And for a polygonal scatterer, it is given in the schematics. As soon as you have a polygonal scatterer, there are two things. There is a straight edge and there is a vertex. So there are vertices are all singular points. And so if we have this, this beam, it can enclose number of vertices. It could be a distance t from this vertex and an s from that vertex. And so I'm saying that there are a number of parameters which are much more than the case of a circular scatterer, where there is a single radius and it's okay. But the formula for connecting the rho plus and rho minus is this one. So that is the one, that is one result, that we have a formula which gives us a collision rule. We were quite surprised that this formula is not in literature known. And this formula actually goes in the limit of the number of sides going to infinity, and it is tending to a circle, goes back to the Gauss's formula. So Gauss's formula is sitting at the edge of this, this formula with the number of vertices going to infinity, and that has been tested. So this is, and so what we do is we conduct numerical experiments and find the distribution of the outgoing radius of curvature rho plus over the radius, the length scale A, which is the largest diagonal. There is a way to define that length scale in a polygon, and that distribution has a mode which goes to half, and this half is actually is this. So if rho minus is very large, which is for a very narrow beam, then this term is very small, and phi becomes very small. So if phi becomes very small, then rho plus is approximately a by 2. So in the limit of a very dilute gas and sparsely placed scatterers, this formula will eventually goes to the right limit. So this is simulation using the polygonal scatterers, and this is the number of vertices. So n goes to infinity, this becomes a circle, and these all mode of that distribution goes to half, which is the right value. The variance goes to 0. So, and we have the distribution. The next point of the talk is of this, I mean not talk, whatever discussion, is that the Lyapunov exponent for the Lorentz gas had been an open historical problem started by Krylov in early 30s, and there's a book in 1940 around that time by there's a relation given by Krylov, and an expression for the Lyapunov exponent for Lorentz gas was found by Hank van Byren and Dorfman in 95 using this expression, which is the velocity divided by the mean radius of curvature. This mean is over I, and I is the number of collisions as the system, as the dynamics progresses. This has to be appropriately averaged. The real average will have to be done over something like Sinai-Ruel-Bowen measures, but that's not what you do. You instead do kinetic theory calculation. So this is based on a kinetic theory calculation, and this is how the expression looks like. A is the radius of that circular scatterer, just to remind you. V remains fixed, V doesn't change, gamma is Euler-Mascheroni constant. So there is a nice calculation, which is in a Reb Letter's paper of 95. Now, we have this task of trying to give an exponent for Ehrenfest gas. Now, in the case of Ehrenfest gas, what happens is that there is a subtle difference between these two systems. You can take a very narrow beam and go on making successive collisions, and this beam can go on nearly indefinitely without any great change of the nature of scatterer that you have. But in the case of polygonal scatterer, no matter what is the size of this beam, eventually there will be a beam splitting at a vertex. And the beam splitting at the vertex leads to a discontinuous change now, and then the rules have to be done differently. So in a very schematic setting, the radius of curvature, if we plot as a function of time, goes on increasing linearly for Lorentz gas because the beam is just spreading, so the radius of curvature is just increasing, and then there is a collision, and then so it is reset, and again it goes on increasing, and there is a reset goes on, and that this continues. This is how this situation for Lorentz gas. For Ehrenfest gas, this radius of curvature increases, and then there is a collision. So if they stay together, it increases. But then the moment there is a splitting at the vertex, this terminates. And so to define a Lyapunov exponent for a system like Ehrenfest gas by making an infinite time average becomes meaningless, because you can't average beyond this point of time. They have split, and they are now two different conditions, two different, I mean, they are not together in any sense to be talking about Lyapunov exponent anymore. So that definition is not correct. It was well known in literature that we have to generalize what is called a Pessin's theorem, which was that the Kolmogorov-Sinai entropy is equal to the sum over positive Lyapunov exponents, and their difference is the escape rate, as was known to a lot of people, including Gaspard and earlier Grasberger and many others. Anyhow, so it's best to define a finite time exponent with the same definition as we have for the Lyapunov exponent, but only go up to a finite time. And then we have a complicated thing. This finite time you can do, right? But then there are many parameters. As we saw in that figure where I showed the collision rule, there are many figures, and we need to average very appropriately over different distributions for all those quantities. Fortunately, and those things we can do. That's a technical part which I'm not doing. That's in our work. Fortunately, it's known, well known, that dynamics between these straight-edged scatters is given by what is called interval exchange transformations. And very recently, in 2014, Arthur Avila was given Fields Medal for the work, which also implies that the dynamics induced by IET, interval exchange transformation, is weakly mixing. And this weak mixing implies ergodicity by a theorem of Sinai. And because this implies ergodicity, we can perform these averages very quickly and very nicely. And so initial conditions become irrelevant, and we can actually define a finite time exponent. The only task now remaining is to show that this finite time exponent, as a function of size, as a function of density of scatterers, this is density. So remember, we are in a plane, so density per number of scatterers per unit area. So this is the expression for Lyapunov exponent for the Lorentz gas, and this is the one for 12-sided polygons for the Ehrenfest gas. And as this becomes something like 1200, this goes on approaching this expression and becomes exactly the same. And we have done detailed investigations of showing how is this convergence established and how actually it happens. And so indeed, the finite time exponent is a logical counterpart of the Lyapunov exponent for Lorentz. And so with that, thank you. Just one remark. The chaotic dynamics in the Lorentz gas is due to the stretching and folding. The interval exchange transformations in the Ehrenfest gas is analogous to shuffling and cutting of a deck of cards. And like it is similar as fluid mixing is to granular mixing. So with those remarks, I would like to thank you for your patience after so many talks, and have a nice day.
Any questions?
Yes, sir.
The finite time Lyapunov exponents are, sorry.
Who is the questioner?
Questioner is here.
You are here.
So the question is, what is the finite time that you have actually taken? I mean, the finite time depends obviously on the time.
Finite time is up to the time the beam splitting occurs. And that depends on the initial conditions.
But you're doing an average over initial conditions.
That is the, yeah, we have to do an average in a systematic manner. There are parameters and we perform those averages.
So what happens if when this time is extrapolated? Obviously it should go to zero. So
it doesn't go to zero.
But you said that there is no finite Lyapunov exponent. Long time Lyapunov exponent is zero, right, for this Ehrenfest gas?
The Lyapunov exponent is exactly zero.
Right.
The finite time exponent is finite.
Right, but it should zero. But it should approach zero as your finite time is going to infinity. So
the finite time does not go to infinity. So if so there is a picture which I did not explain. So these are various strides of our particle dynamics. So if I just perform average over one of them, just one of them, I get the lowest bound, and that is already non-zero. So finite time exponent is strictly positive.
We have talked. Thanks. Thanks.
Just a curiosity, is there any sort of analog of the Gauss's formula for the Lorentz gas in 3 dimensions?
3 dimensions? Yes, it is. There is a spherical mirror.
And the Lyapunov exponent has been calculated in 3D?
I think there is a gang which did this. I don't remember.
So can you put extra conditions and show it's mixing?
It cannot be mixing.
It cannot.
It's just weakly mixing.
Weakly mixing.
Extra condition means I should change the system.
Yeah. Because mixing is very strong. That's why.
Yeah, this is weakly mixing.
Yeah, I understand.
Yeah,
Weakly
so,
mixing.
no, you know, I think more than me in this case. So, but no, I don't know what to do. Yeah, you can change the curvature, but then that's changing the problem. Yeah, so I don't want to do that.
Just thank the speaker again.
Thank you. Thank you.
I think that this session ends here. So.
Yes, okay, so let's thank Paul for chairing the session, and we'll meet again.